Hello, you're viewing part of a video lecture series for GG413 Geological Data Analysis at the University of Hawaii. In this video, I'd like to revisit our linear least square regression applied to a line as our regression function. And in this video, I'd like to cover how to compute the confidence intervals on the slope and intercept of the line, as well as a confidence interval for each point along the true regression line. And this lecture comes from uh, presentations in John Davis's book, Statistics and Data Analysis, and heavily from a textbook by Draper and Smith on applied regression analysis. So as you well know, the Hawaiian island chain is formed by a hotspot centered beneath Kilauea, and the volcanoes form as they sit on the Pacific plate as it moves away from the hotspot. And this, of course, gives rise to volcanoes that are progressively older as you move back along the chain. Now, the diagram to the right shows radiometric ages of many lava samples taken from 4 volcanoes: Ni'ihau, Kauai, a submarine swell just south of Kauai, as well as West Kaiana, which is just off of Kaiana Point of Oahu. And the younger ages here are rejuvenated lavas, and let's not consider those, but we'll focus on the tholeiites, which are at the older ages. And as you can see, there's a tendency for each cluster of ages to increase as you move um, further away from Kilauea, the horizontal axis being distance from Kilauea. And this is well explained by this motion of the Pacific plate over the fixed hotspot. But in addition, that's not the only thing that controls the ages of these lavas. As you can see, there's variability at a given volcano about what might be the true linear trend. And that variability is related to the eruptive history of individual volcanoes. That's not um, that's sort of not directly associated with that true linear trend caused by the plate motion. So let's begin to formalize our problem here. And our data are x, this is distance from Kilauea, and y, which is our age. And again, this is our pair of data that we collect for each rock that we date, and in this case we have lots of rocks and lots of data pairs. And so the age of each of our lava rocks is influenced by the plate moving over a fixed hotspot, and it's also influenced by local eruptive processes. The local eruptive history of each volcano. And we can describe that as the sum of a true line regression with an intercept of alpha 1 and a slope of alpha 2 at each volcano location x plus epsilon. And epsilon describes everything not related to this true trend, and we could refer to that as noise, or in this case, the local eruptive history. Now, of course, we don't know the true linear trend. We can only estimate the trend. Estimate that trend. And of course, we estimate with our model line, which has a model intercept or an estimate of alpha 1, which is what we call A1, an estimate for the slope, which is A2. So you can imagine how the estimate of the true linear trend is completely dependent upon how much noise there is in the data, as shown by the scatter about the linear trend of these ages, right? It's also dependent on the number of data points we have. So when we formulate the problem like this, we're assuming that x is perfectly known. So we're assuming that we know the location of each volcano relative to the hotspot, and that all the uncertainty is related to this epsilon term. And epsilon can the scatter of associated with epsilon is going to be characterized by a variance sigma I squared for each volcano. Okay, so each volcano has a variance associated with the processes not related to this, uh, the plate motion over a moving hotspot. And in this analysis, we're going to assume that this variance, this variance is constant for each volcano. So sigma squared will be the variance about the linear regression trend for all the volcanoes, which is constant. So the other factor that's going to influence our uncertainty, of course, is the number of data points. This shows a situation where we have a lot of data, but oftentimes the situation occurs where we have a lot less data, such as what I show here. And so you can imagine that a case with a lot less data will lead to larger uncertainty of our regression line. Okay, so again, we're looking to define the confidence interval, the slope, intercept, and each point along the true regression line. So let's look at the solution. So this is what the solution looks like for the regression line itself. But first, the slope, let's address the slope. So the variance of the slope, or the standard deviation of the slope, we'll call that sigma A2, and that's, of course, the square root of the variance of A2. And the solution for that is sigma. It depends on sigma, the variance of all the data about the true linear trend, times 1 over the sum of all our distances, or the sum of all the differences of our locations from the mean distance. And instead of a bar for mean, I'm going to use a hat for the mean, because I don't want to confuse that symbol with the vector x. So x hat is the mean of our measured values of x. And so this term is the sum of the square deviations from the mean of x. And this gives the standard deviation of the slope. And therefore the confidence interval is given as, so alpha 2 is somewhere in the range. Well, it's centered near our best estimate for alpha 2, plus and minus our standard deviation of our estimate of our model slope, times t, our t statistic for 1 minus our significance level, 1 minus half our significance level, and our number of degrees of freedom are n minus 2. and we subtract 2 because we're estimating alpha 1 and alpha 2 in our regression. Okay, so that's the solution for the confidence interval on our slope. So let's look at our intercept. And the standard deviation of our intercept we'll denote that as sigma A1. And that too depends on sigma, the variance or the standard deviation of each about the regression line. So it's proportional to sigma. And it's multiplied by the sum of all our x values squared divided by n times the sum of our squared deviations from the mean value of x. And that's all taken to the 1/2. That's our standard deviation. The variance, of course, would be this, everything squared. And the confidence interval on our intercept, therefore, is alpha 1 is equal to our best estimate, which is A1, plus and minus our standard deviation times our t value, again, at a significance level of alpha and degrees of freedom of n, the size of our sample, the number of data pairs we measured, minus 2, because we're estimating 2 parameters in our regression. And the last part of our solution is the confidence interval on the true linear trend itself. Or a true line, so to speak. So the standard deviation of each model value of our line, y sigma sub y m sub I for each point of our model. Okay, that's the square root of the variance of each point of our model. And that too is going to depend on sigma, the deviation or the deviation of all our data about the true line. And the function here is 1 over n plus the squared deviation of x from its mean square, right, the square deviation divided by the sum. And I'm going to write a sum over k just to distinguish each point in this sum from the ith value of x above. Okay, so the numerator is the sum of the square deviations of x from its mean. And that's all taken to the 1/2. And so the confidence interval on the true line, right? So I'm using mu to denote the true line function, is equal to our best estimate, which is our model function, plus and minus this confidence interval, sigma y m I, times, again, our t statistic. Okay, so what I show here, the solid line is YMI, our best fit line, and this is YMI plus sigma YMI times T. and this is YMI minus our uncertainty. Okay, so this is the solution. But one thing you might have noticed is that we're using the true value of the standard deviation of our noise. And we don't often know that. Well, we don't often know that. So we must estimate sigma. And we do that by taking, so, so we'll estimate sigma as S, the standard deviation of the noise about our best fit line. And that's equal to the sum over all our data points, all our ages, or all our Y measurements, minus our linear regression value. So we're summing the square deviation of all our data from the regression, and that's n divided by n over 2, all taken to the 1/2. And what that is just our RMS misfit. So in practice, when we produce our solution, we'll substitute the sigma with our estimate for sigma, which is S. And that's true for the linear regression as well as the sigma that appears for our intercept as well as our slope. Okay, so that's the solution. And I think maybe I'll stop this video here, and in the next video we'll cover how we got those solutions.